Okay, this first lesson is just a quick review of some of the basic concepts that we need for algebra. The first is the idea of a set. A set is a collection of objects which are called elements here. Elements usually for us in algebra class are numbers, so an example of a set would be the set that consists of the elements 1, 2, 5, 7. That's a set, and the elements in the set are the 1, 2, the 5, and the 7. When we solve an equation, let me fix that. When we solve an equation such as x minus 3 equals 5, we get a solution of 8. Most of the time the book will ask you to write the solution in a solution set, and so we would put the answer in those little brackets. This is called the solution set. Some equations have more than one solution. For instance, this one has the solution 0 and 5. And so I would put both of the answers in the solution set. Now, set builder notation looks like this. This means the set of x, or the set of all x's. The bar means such that x has this property. For example, all x's such that x has this property. X is an even number between 5 and 11. So you're looking for all the numbers, all the x's that meet this requirement. All the even numbers between 5 and 11 would be 6, 8, and 10. And so this is the same as the set 6, 8, 10. Here's another one. All x's such that, remember that this bar means such that, x is a multiple of 5 greater than 0. Now, multiples of 5 that are greater than 0 would be 5, 10, 15, 20, and so on. And so this would be the set 5, 10, 15, 20. Continuing in that fashion, I put some dots here like that, showing that it does go in this manner. Sets that go on like this forever have an infinite number of elements in them are called an infinite set. This is an example of an infinite set. One more example of set builder notation. All x's such that x is a positive number less than negative 3. So what numbers are positive and less than negative 3? There are no such numbers, and so there are no answers to this. And so this is what we call the empty set. If it had an answer, I would put it inside there, but there are none. It's empty. We have a symbol for this. It's a 0 with a line through it like that. That means empty set. Whatever you do, don't do this to represent an empty set. Because that set is not empty, it actually has the value 0 in it. So you can't use a 0 to represent that a set is empty. Not the same thing. Not the same. as the empty set symbol. Okay. Now for some sets of real numbers that we have. The natural numbers is probably the simplest set of numbers. If someone asked you to start counting, you would start at 1, and then go 2, 3, 4, and so on. That is the set of natural numbers, and for obvious reasons it's also called sometimes the counting numbers, so known as the counting numbers. If you include 0 in this, start at 0 and then go 1, 2, 3, and so on, like that, then what you have are called the whole numbers. So there's not much difference between natural numbers and whole numbers. As a matter of fact, if you take, for instance, the number 5, the number 5 is both a natural number and a whole number. Next is the integers. If you take whole numbers, excuse me, if you take whole numbers along with their opposites, such as 0, 1, 2, 3, and so on, and then -1, -2, and -3, continuing like this, then you have the integers. What's not in here yet are things such as fractions and decimals, and they come into play with the rational numbers and the irrational numbers. Now, rational numbers are numbers that can be written in this form using our set builder notation here. Rational numbers are the numbers that are of the form P over Q such that, or provided that, P and Q are integers. Q cannot be 0, however. We can't divide by 0, which we'll talk about later. So you take any two integers, so provide that 0 there, and you write them as a fraction, and you have what's called a rational number. So, for example, -2 over 3 is a rational number because it is the integer -2 over the integer 3. The number 7, even though it doesn't look like it, is also a rational number because you can write it as 7 over 1. That means that all the numbers that are above rational numbers, the integers, the whole numbers, and the natural numbers, are also rational numbers. Even 0 can be written as 0 over 1, and so it is a rational number. Even decimals, such as 0.37, the decimal 0.37 can be written as the fraction 37 over 100, and so that means that it is a rational number as well. 0.3 bar, you may recall from previous math class, a bar over this number here means that that number repeats itself. So this is actually 0.3333 and so on, so on, so on. And it turns out that that repeating number can be written as a fraction. It is the fraction 1/3. And so 0.3 bar is also a rational number. So any number that you can write as a fraction, or the quotient of two integers, some books say. I'll put that right here, quotient of two integers. Then you have a rational number. All decimals that either terminate, such as my 0.37 example, that's a terminating decimal. It goes to two decimal places, then it stops. All terminating decimals are rational numbers. You can always write them as a fraction. And repeating decimals as well. Terminating decimals and repeating decimals can always be written as a fraction, and therefore they are rational numbers. Now, what does that leave us here? Well, irrational numbers are all the numbers x such that x is not rational. There are some numbers that you just can't write as the quotient of two integers, and I guess the most famous one is probably the number pi. Pi is a decimal, or written as a decimal, would go on randomly forever, 3.141592, and so on. It does not terminate, it never stops, it just keeps going, it's infinitely long, and it never repeats, it never starts repeating itself, and so it's a non-terminating, non-repeating decimal, and that makes it irrational. So I'll write under here, irrational numbers are non-terminating and non-repeating decimals. Another example would be square root of 3. If you type the square root of 3 in your calculator, you get a decimal. You don't see all the decimal, but if you could, it would go on randomly forever, non-terminating and non-repeating. And other square roots, such as square root 5 as well, would be an irrational number. All right. So real numbers, what are real numbers? Real numbers consist of your rational numbers and your irrationals. You put your rational numbers together with your irrational numbers, and what you have is the set of real numbers. Within rational numbers, you have integers. Within integers, let me fix that. Within integers, you have whole numbers, and within whole numbers, you have natural numbers. So for instance, the way this works here is if you have a natural number such as the number 5 is also a whole number, it's also an integer, it's also a rational number, makes it a real number as well. 5 is all of those. It's everything except the irrational. Square root of 7 is an irrational number, and it is also a real number. A number such as -3 is an integer. It is also rational, and it is also a real number. It's all three of those. Here's some more examples of that. -6. -6, first of all, is an integer. It is a rational number. So you could write as -6/1. And it is a real number. It's all three. The number 12 is a natural number. It's a whole number. It is an integer. It is rational. And it is a real number. It is all of those. 0.5 bar. That means 0.555555 repeating. And we learned that all repeating decimals are rational numbers, and it is also a real number. Negative square root 10. Square root of 10 is irrational and a real number. (22/7), well, that's the quotient of two integers, written as a fraction. And so that makes that a rational number and a real number. 3.87, that is a terminating decimal, and so it is a rational number. All terminating decimals are rational, and it is also a real number. So everything that we're dealing with now is a real number. Those of you that have taken an algebra class before may have heard of imaginary numbers, but we're not worrying about those right now. We talk about those in a much, much later chapter. So everything that we work with now is a real number. Okay, moving on. Let's do a quick review of absolute value. Now, you may remember that absolute values, here's the symbols. What absolute values do is they make everything positive. For instance, the absolute value of 3 would be 3. It's already 3 is already positive. The absolute value of 3 would stay positive. Positive 3. Absolute value of negative 3. The absolute values make it positive, so that's also 3. One way to think of absolute value is like this. The absolute value of A is the distance from 0 to A. Oh, let me fix that. On a number line. So if I have a number line here, let me give you an example of 3, a negative 3 here. Supposing I want the absolute value of 3. Well, here's 3 on the number line. How far away is 3 from 0? Well, it's this far away. 3 units away. Distance is always positive. So that's why the absolute value of 3 is 3. The absolute value of negative 3, well, here's negative 3 on our number line. Negative 3 right here. How far away is negative 3 from 0? Well, it is the distance 3 as well. Distance is always positive. And that's why the absolute value of negative 3 is also 3. The actual definition of absolute value, though you don't really need it to calculate an absolute value, is this. The absolute value of A, if A is positive and the absolute values do nothing at all, the answer is just A. So the absolute value of A is just A, if A is greater than or equal to 0 to begin with. However, if A is a negative number, if A is something negative, then what do the absolute value signs do to it? They make it the opposite of that. And so they multiply it by negative 1. That looks deceptive there. That looks like a negative number, but it's actually positive. It's actually the opposite of a negative number, such as if A were negative 5, the opposite of negative 5 would be positive 5. Here's some more examples. For instance, the absolute value of negative 5 would be 5. The absolute value of 7 would be 7. The absolute value of negative 8/3 would be positive 8/3. Absolute value of 0 is, of course, just 0. Okay, so even though that these are some slightly more complicated ways of thinking of absolute value, absolute values just make things positive. Here's a couple more examples of using absolute values. Absolute value of, I'm sorry, negative absolute value of 2. The negative sign is on the outside, and so what I'm going to do is I'm going to think of that as a negative 1 times absolute value 2. That's really what it means. Now that's negative 1 times absolute value of 2, as we learned, is just 2. Answer is negative 2. Negative absolute value, negative 7. That negative sign on the outside, I'm going to write as a negative 1 again, just like I did on the previous example. Now I'm going to calculate the absolute value of negative 7, which is a positive 7. And negative 1 times a positive 7 is negative 7. All right, next one. Absolute value of negative 6, positive 6. Absolute value of negative 3, positive 3. Add those together, and we get 9. Next one. Absolute value of negative 9 is positive 9. The absolute value of negative 4 is a positive 4. Notice I still have this minus sign right there. 9 minus 4 is 5. There's our answer. One more with absolute values here. Negative absolute value 9 minus 4. Figure out what you have in the absolute values first. 9 minus 4 is a 5. So this really means a negative 1 times absolute value 5. That's a negative 1 times a 5. Oh, let me change that. That's just 5. I don't need absolute values there anymore. Negative 1 times 5 is negative 5. Okay, there's a quick review on absolute values. Next on our review here is inequalities. Meaning symbols that are not equal. The first one is the not equal to sign. It's an equal sign with a slash through it. It means not equal. We don't use it that often. An example of it would be 3 is not equal to 5. Less than. For example, negative 4 is less than negative 3. The point always points to the smaller number, or the inequality symbol opens up to the larger number. Greater than. An example of greater than would be 5 is greater than negative 1. Notice that the symbol, the greater than symbol right there, opens up to the larger number. We also have the less than or equal to sign. Less than or equal to. An example of that would be negative 10 is less than or equal to negative 7. You could also have them actually equaling here. For instance, negative 7 is less than or equal, it is equal to negative 7. So these would both be correct statements, true statements. And then we have the greater than or equal to sign. And an example of that would be 3 is greater than or equal to 3. 7 is greater than or equal to negative 2. A couple examples of that using that symbol. Okay, next. Exponent review. Four cubed. 4 cubed means 4 times 4 times 4. And that is if you multiply that together, you get a 64. Negative 4 cubed means negative 4 times negative 4 times negative 4. Multiply those together and you get a negative 64. Now compare that to negative 4 with no parentheses and then cubed. A little bit different. The only thing being cubed here is the 4. The negative sign is not being cubed. You want to think of this as negative 1 times 4 cubed. Negative sign is not being cubed, as I said. Well, that's negative 1 times a 64. Negative 64. Now you might think, well, I got the same answer here and here, so it doesn't matter whether I have parentheses or not, but actually it does. Take, for instance, this example, or these two examples. On the first one, the negative 5 squared, no parentheses, actually means negative 1 times 5 squared. The only thing being squared there is the 5. The negative 1 is not being squared. So this is a negative 1 times 25. That's a negative 25. On the other hand, this one with the parentheses, the negative sign is inside the set of parentheses and it is being squared. This can be thought of as negative 5 times negative 5, which is a positive 25. So notice the parentheses are important here. One gave me a negative answer, one gave me a positive answer. Another example of that situation would be this. Negative 3 squared, no parentheses, means negative 1 times 3 squared. That's a negative 1 times a 9. That's a negative 9. This one is negative 3 times negative 3, which is a positive 9. I guess I should do one of these as well. The negative sign on the outside, I'm going to write as a -1, like that. Now we have -4 in parentheses and it's being squared, and as we've just seen, we've talked about this, that's going to be a positive 16 because it's a -4 times a -4. So that's a -1 times a positive 16. And so this solution here, this answer is -16. Okay, it's just a quick review of exponents there. Let's now make a mention of square roots. First example, square root of 9. The square root of 9 is 3. And the reason for that is if we take 3 and we square it, we're going to get 9 back. Likewise, the square root of 25 would be 5. Because if we take 5 and we square it, we get 25 back. Negative square root 16. Notice the negative sign's on the outside, and so I'm going to write that as a -1. This means -1 times square root 16. That's -1 times 4. Square root of 16 is a 4. So this is a -4. The negative sign on the outside made the result negative. Compare that to square root -16. Now, what number can you think of, a question mark there, what number can you think of when you square it is going to give you -16 back? Well, there is no such number, no real number that does that, because anytime you square a real number, you're going to get a positive answer. So there's no answer to that. And so what we're going to say here is that this is not a real number. Those of you that have seen imaginary numbers before know that you can actually answer this, but we're not even close to doing that yet. So you cannot, at this point, take the square root of a negative number. You want to write not a real number. Another example of that would be square root of -36. Since it's the square root of a negative number, can't do it, not a real number. All right, just a couple more examples of square roots. The square root of 9 over 16, 3/4, because if we take 3/4 and we square it or multiply it to itself, 3/4 times 3/4, we'll get a 9 over 16. And we also have one more here, two more. We got square root of 0 is, of course, 0. Square root of 0 is 0. And one more example. Negative square root 1/4. The negative sign is on the outside, and so that's a -1 times square root 1/4. Square root of 1/4 is a 1/2, because if we multiply 1/2 to 1/2, we get a 1/4. And so this is a -1/2 as our answer. Okay. One more thing to mention here for our little review, and it is division by 0. Division by 0 is undefined. Division by 0 is undefined. Can't do it. And here's why. If we take 6 divided by 2, we know that's 3. And the reason for that is because if we take 3 and we multiply it to 2, we get back 6. Similarly, if we take 10 and we divide by 5, we get 2. And that is because if we take 2 times 5, we get back 10. That's why 2 is the answer. We can even have 0 divided by 3. 0 divided by 3 is 0. Because, if I follow the same reasoning, if I take 0 times 3, I get back 0. this times this gives me that. However, I cannot do this. 3 divided by 0. Now what is that? Well, if it actually had an answer, then I'd have to be able to do this. That, whatever the answer is, times 0 would equal 3. Now, what number times 0 is going to give you 3? There is no number that does that. It's impossible. And so what we're going to write here is that this division problem is undefined. Undefined. Okay, anytime you divide by 0, it is undefined. Here's another example. 7 over 0 would be undefined. Negative 5 over 0 would be undefined. And even 0 over 0 is undefined. However, you can have 0 in the numerator. That's okay, as long as the denominator is not 0. And that is the reason why division by 0 is undefined in mathematics. And that ends our quick review of some of our basic concepts.